Hello and welcome back for some more reinforced concrete design. In this tutorial, we are going to first summarize quickly how to approach designing a singly reinforced beam and then fully solve an example, looking at a few different options along the way. Let's get started. Before we move on to the worked example, this flowchart summarizes the full design process for a singly reinforced beam. Every step shown here is directly built from the Eurocode equations and the theory we already covered in the lectures. All the underlying derivations, assumptions, and limits have been fully explained previously, so this flowchart simply brings everything together into a practical step-by-step procedure. We start by determining the design actions and calculating the bending moment, MED. The first check concerns the concrete class. For concrete up to C50-60, we can use the simplified rectangular stress block exactly as we derived it in the lectures. For higher strength concrete, the coefficients lambda and eta must be calculated according to Eurocode 2, which leads to a slightly different solution path. Next, we calculate the non-dimensional parameter K. From the lectures, you'll record that K tells us how heavily the section is stressed in bending. We then compare it to the limiting value K tag, which represents the maximum neutral axe depth before compression failure would occur. If K is larger than K tag, the concrete alone cannot carry the compression and compression reinforcement is required. If K is below this limit, the section can be designed as singly reinforced. Once this is confirmed, we calculate the lever arm Z using either table 3.4n or the expression shown on this slide, with a reminder that Z cannot exceed 0.95d. Once Z is known, we can determine the tension reinforcement from AS equals MED divided by 0.87 FYK times Z. And at this stage, we can also check the minimum and maximum reinforcement requirements as stated in the code. Finally, we convert the steel area into a practical bar layout. Select the number and size of bars, check the spacing requirements, and ensure the arrangement fits within the available width while meeting the detailing rules, such as minimum clear spacing based on aggregate size. This flowchart provides a complete roadmap, and we'll now apply it step by step in the worked example. For our first worked example, we'll design a simply supported beam subjected to uniformly distributed loading. The beam spans 8 meters and carries a permanent load including self-weight of 7 kN per meter, together with a variable load of 5 kN per meter. The section breadth is 250 millimeters. We'll be using concrete of a strength class of C2530, and the reinforcement has a characteristic yield strength of FYK equals 500 megapascals. Our aim is to design the beam at mid-span. To design the reinforcement in this example, the process is broken down into a series of straightforward steps. We begin by determining the design load and calculating the ultimate bending moment at mid-span. Once the moment is known, we can calculate the required area of tension reinforcement. This includes choosing the number and size of bars that provide at least the area we calculated. After that, we can select an appropriate concrete cover, and finally, we bring everything together by calculating spacing, checking the detailing, and producing a clear drawing of the beam design, showing the reinforcement layout and all the relevant detailing. So, let's get to it. So here you can see the solution on calculation sheets. Calculation sheets always have a title block at the top with all the relevant details of the project, the checkers, and so forth, and 3 main columns. The left-hand column includes references, for example, the parts that you've used in the code or where you've taken data from. The middle column will have calculations that you write, and in the right-hand column is the output, the results that you're taking forward. Here I've started by adding my input, so the length of the span of 8 meters, the breadth of the section, which is 250 millimeters, the permanent and variable loads, which were 7 kilonewton per meters and 5 kilonewton per meters, the strength of the concrete and the strength of the steel. We start off by finding the design load and the ultimate moment. The design load really is the permanent load, which is 7 kilonewtons per meter, times the partial safety factor for permanent loads, which is 1.35, and 1.5, which is the partial safety factor for variable loads, times 5 kilonewton per meter, which is the variable load. And this gives us an ultimate design load of 16.95 kilonewtons per meter. Now, since this is a simply supported beam, finding the bending moment is pretty easy. It's going to be the load that we found, 16.95, times L squared, which is the span squared, which is 8 meters in our case, divided by 8. This is a known equation, but if in doubt, you can always figure out the reactions and calculate this yourself. But we end up with a moment of 135.6 kilonewton meters, and this is our design moment. Now, in this example, I have not been given the height of the beam, meaning that as part of my solution, I also need to find the height of the beam. So given that we want a singly reinforced beam, I can look to the value of K. K, if you remember, was the limit that shows me if my beam can be singly reinforced or has to be doubly reinforced. And K equals the moment divided by the strength of concrete times B times D squared, where B is the breadth of the section and D is the effective depth. Now, I can swap this around to isolate D, the effective depth, because I have no idea of the height, and find out that it's a square root of m divided by FCK times B times K. Now, I know that the limit in K is 0.168 as per the UK recommendation, and that'll give me the minimum effective depth to avoid using compression steel if I substitute it here. Now, this would not suit if I had already been given a height of the beam. If I have the height of the beam, I then need to find if the K in that beam is suitable to be singly reinforced or if I need to do compression reinforcement. But in this case, since I've not been given height, I can find out this minimum D. I know the moment, 135.6, we just calculated it, times 10 to the power of 6, this is to organize my units, because my moment is in kilonewton meters. My FCK, the 25, is in megapascals, which is Newton per millimeter square, and the breadth of the section is in millimeters. So all in all, I'm organizing my units to get to an answer in millimeters. And I can find out that the minimum effective depth that I need for my section to make sure that it's singly reinforced is 360 millimeters. Once I know that, I can calculate the lever arm, because for that I need D, which I know, 360. And then within the brackets, really, all I need to know is K. So I've got 360 divided by 2, and then in brackets 1 plus a square root of 1 minus 3.53 times K, which we're taking as the limiting value of 0.168. And I get that Z, the lever arm, is 300 millimeters. If I know that, I can find the area of steel required, and AS required is going to be MED, that design moment that I found, divided by 0.87 FYK, that is the strength of steel, multiplied by the safety factor for steel, and times Z, which I just found as 300 millimeters. And if I do that, I find out that the required area of tension steel is 1039 millimeters square. Now, it's really interesting to note that we calculated the minimum effective depth required for no compression reinforcement. Any smaller than that effective depth, and we would definitely need compression reinforcement. However, what we could do is we could take a bigger effective depth, and that way we would lower the area of reinforcement required. So let's see what happens, for example, when we take D, effective depth, of 400 millimeters. In that case, we can calculate K just to make sure. So the moment divided by FCK times B times D squared, and we'll find that K equals 0.136, which, just as we expected, is under the limiting value of 0.168. If we calculate Z this time, we will find out that the only thing that's changed is really D and K. So substituting the D of 400 and the K of 0.136, we end up with a Z, a lever arm, of 347 millimeters. Now, we always need to check if that lever arm is under 0.95D. If it was not, we would take the limiting factor of 0.95D. In this case, it is, and therefore the lever arm remains 347 millimeters. And therefore, we can, just as we've done previously, calculate the required area of reinforcement. The moment has stayed the same, 135.6 kilonewton meters. The strength of steel is the same, and the only thing really that's changed is Z, the lever arm, at 347 millimeters. Now just remember that 10 to the power of 6 is to organize my units. And if I do that, I end up with a required area of steel of 898 millimeters square. So this is much smaller, so I can see by adding to my effective depth, if I can, I can't always, there's sometimes are limitations, I will get a smaller area of reinforcement. And if we assume, for example, a diameter of 20 millimeter bars, then we can see that the number of bars is the total area of reinforcement required, 898, divided by the area of 1 bar of 20. We get 2.85. Obviously, we must never take less reinforcement than we need to. We will always round up. So here we will round up to 3 bars, and then we can calculate the actual steel reinforcement that we provide, which is 3 times the area of 1 bar of 20, and we end up with a provided area of 943 millimeters square. Now, there isn't just one solution for this required area of steel of 893 millimeters square. So we can look, for example, at this table. This table shows us in the columns the bar diameter. So you can see here 6 millimeter, 8 millimeter, right up to 50 millimeters. And here somebody's already very kindly calculated for us the area of 1 bar, of 2 bars, of 3 bars, up until 10 bars. And this allows us, if we don't already know that we need bars of 20, to come in here and pick out different options. So for example, as we saw, 3 bars of 20 give us the required amount of reinforcement, but so do 2 bars of 25 and 5 bars of 16. So you can see here there are quite a lot of options that will answer that required area. So just to summarize, we could have taken 5 bars of 16 diameter and we would have gotten 1005 millimeters square reinforcement, or we could have taken 2 bars of 25 and we would have had around 982 millimeters square of reinforcement. Both would have been valid answers given that they would have suited in terms of different things like detailing and spacing. If we continue with our assumption of 3 bars of 20 millimeters, and we assume that our secondary steel or our steel links are 8 millimeters, we can now check the min-max reinforcement requirement. So from the Eurocode, FCTM for our strength of concrete is 2.6 megapascals, and therefore AS minimum, the minimum area of reinforcement, will be the max of 0.26 times FCTM, which in our case is 2.6, divided by FYK, the strength of steel, which is 500 in our case, or 0.0013, both these times B times D. And if we take the maximum of those, it works out as 135 millimeters square. The maximum area of reinforcement allowed is 0.04 times B times D, and that gives us 4,000 millimeters square. And in our case, we can see that the area of our reinforcement is in between the min and maximum. So we have passed this check. We now need to find the concrete cover, and this is because we weren't given the concrete height. We've started with the effective depth, and we're working our way back to the height of the section. So assuming an exposure class of XC1 and a structural type of S4, the durability works out to be 15 millimeters. And I'm just going over this quickly because we've already done cover, so no need to waste too much time here. The cover for bond is going to be the minimum cover for the stirrups or the secondary reinforcement, which we've decided is 8, or the bars, which we know is 20. And in general, the cover is going to be the minimum cover, which is going to be the max between the durability or the bond, which we've just defined, or 10 millimeters, plus the standard deviation, which according to the UK National Annex is 10 millimeters. And that'll give us the cover. So in our case, if we take the stirrups with a bond of 8, we get a cover of 25 millimeters till the stirrups, or if we take the main bars with a bond of 20, we get 30 millimeters till the bar. The deciding factor really for us is going to be the cover to the stirrups, because if we take that, so we take the 25 millimeters to the stirrups or till the secondary steel, and then add the secondary steel, which is 8 millimeters, we get that we have a cover of 33 millimeters before we hit the main bar, which is more than the 30 millimeters which just came out of the equation. So we're going to go with the stirrups designation of 25 millimeters cover before we reach the stirrups. Before we finish, we do need to check that the cover is fine for fire. We'll just assume 30 minutes resistance time, and we'll need to look for this in a different part of the Eurocode. So up until now, we've mainly been focused on Eurocode 1992-11, and here the fire cover is actually in 1-2. Now, for the fire cover, actually, we need a different cover. The cover for fire is until the middle of the main reinforcing bar. So we have a cover of 25 plus the secondary steel, which is 8, plus half of the diameter of the main bar to get to A. If we calculate what A is, it works out as 43 millimeters. We need to compare that to what is designated in the Eurocodes as a minimum cover to provide 30 minutes of resistance time for fire, and that is actually 25 millimeters, so we're fine. And usually you will find that durability and bond exceed the cover required for fire. Now that we have that, we do also need to check the spacing between bars. The spacing between bars is essentially the gaps in between the bars, We need to make sure that that's big enough to allow things like the flow of concrete when we're casting the concrete. The spacing between the bars is B, the breadth of the section, in our case 250, minus the cover from either side, so 2 times the cover, in our case 25, plus the secondary steel, so in our case 2 times 8, plus the number of bars times the diameter of the bars, so 3 times 20. And we always need to divide this by the number of gaps. So if you have 3 bars, there will be 2 gaps between the bars. It's always going to be 1 less than the number of bars. And this works out as 62 millimeters. We do need to check, though, that this spacing is bigger or equal to the diameter of the principal bar, the aggregate size plus 5 millimeters to allow flow, or 20 millimeters. If we assume that the aggregate size is 20 millimeters, we need to make sure that the spacing is bigger than 20, the diameter of the principal bar, 25, aggregate plus 5, and 20. And it works out that 62 is bigger than those, and so the spacing remains 62 millimeters. And now we can really find the height of the section and summarize our design. The height of the section is really going to be the effective depth plus A, or the effective depth plus half of the main reinforcing bar plus the diameter of the secondary steel plus the cover. And in our case, the effective depth was 400, and we already know from before that we had 43 as that A, or the fire, which is the fire cover, or 10 plus 8 plus 25. And that gives us a height of 443 millimeters. Now that would be a very, very strange height to cast, so we would opt for a height that is reasonable, probably in this case around 450 millimeters. And that is how our section would look like. We've got a concrete section of 250 on 450. We've got our secondary steel of 8 millimeters. We've got a cover of 25, and we've got 3 bars of 20 with a 60 with spacing between them. And that is the solved singly reinforced beam. Thanks for joining me in solving this beam. I hope it was helpful, and I hope you join me for some more reinforced concrete design.